The first 3 weeks of the eruption here in Hawaii, crazy things would happen in the middle of the night. A new fissure would open up and it would threaten a new neighborhood. Thousands of people were evacuated from their homes. I started the Hawaii Tracker Facebook group to help people understand what's going on and get their questions answered.
Hey, how's it going? We're live. This is Fissure 20.
We had hundreds of people all throughout the neighborhoods sending in videos, articles, and images. We spend a lot of time making sure the accurate information gets out.
This is live. Still lava moving.
They weren't just sharing a story, they were helping their neighbor. If a family was being evacuated, my group would just jump in and help out. So it was huge. They were watching out for each other.
Hello everybody, thank you for coming. Thank you for the support from everybody.
As we go through this, we're growing closer together as a community. When tragedies like this strike, you really realize how much you need each other.
Hello everyone, I'm Philip Ong, geologist. I'm here with Mr. Dane DuPont. On behalf of HawaiiTracker.com, we're here to bring you guys another Kīlauea volcano update. Today, February 3rd, 2021, the 45th day of this ongoing eruption of Kīlauea volcano. What you guys see here on screen is the latest video put out by the USGS on the current activity. We still have lava coming out slowly from the bottom of the west vent, kind of oozing and a slow pulsing going on. Here's a broader view. There's a west vent island has been stuck. Here's kind of a third view, kind of looking at how everything is entubed and lava is coming out only at the base of the vent here. So just a very brief overview. We're going to go into more detail of all the different features while Dane takes questions, all of our streams. So let us know if there's something that we can answer in more detail for you guys. So yeah, that is essentially the latest view here on Kīlauea. Let's see if there's anything else I can point out. That the whole eastern side of the lake, so on this view there's a levee. We have a trench, a low spot down in here and over here as well. And lava's been spilling into those zones while staying quiet up here at the top. And here's that base of the west vent once again. You can kind of see it's a slow ooze and the pulsing's happening right at that exit point, and you can see that a little bit. Every few seconds it'll rise and then fall and then rise and then fall. And here's that wider view and that stagnant eastern portion of the lava lake that's crusted over but still liquid underneath. All right, so that's the first view we have. The second video we have released is an overflight from yesterday, and that video I just showed you guys was from 2 or 3 days ago. So here's kind of a broader view. You can see there's our west vent once again, putting out all its gas within the summit caldera of Kīlauea, the pit of Hale Ma'u. In a closer view, we can kind of see that western drop block. Western vents here. Northern vent is what remains of it is floating on a lava lake crust over here. Kind of like these other little islands that are all crusted over in this eastern part of the island over here. Right, they're just a bit lower than that active western part. So really all the hottest lava is right in that little zone right in there. And it's spilling over into the trench this way, it's spilling over into the trench this way, and it's going around this island both ways. And somehow going underneath and mixing and putting some of its heat towards keeping that lava liquid that's underneath this eastern crust. That's the dynamics of it more or less in there. So there's our latest videos. And we'll look at the deformation data from USGS Hawaiian Volcano Observatory, who is our source for all these videos and the data we're presenting to you guys today, unless we get to some of the research later. We will do a historical segment today, looking at some of the supply rates of magma to the volcano, and we'll see what that might mean in the long term for our prospects of our current eruption. So we'll start off with the current pressure with a tilt. So looking at the last 2 days, you can kind of see we've dropped down from +1.5 to about -3.5. So that's about 5 microradians so far, and a typical deflation, kind of concave that direction, deflation inflation cycle. Here's zooming out the past week view, so you can kind of see that before that, fairly steady rise, although only in a range of 2 microradians, 2 or 3 microradians or so, and then we've had that bigger deflation since. You really got to zoom out to the last month to really see it, and we're looking at the blue line here in all these plots as a summit station at Uekahuna, and you can kind of see in the last month, we've actually had one of these big events, and then maybe some small ones in here, but really 2 big ones, and a 3rd big one right in here. So this looks to be the 4th sizable deflation inflation event. We'll expect it to do that kind of pattern, and we'll just have to wait and see what happens. It's kind of blown out here by this green line. That's the pool signal on the East Rift Zone. That's showing kind of a big drop that happened kind of coincident with that big rainstorm, so we'll see what that actually means when we get more data from the USGS. But we really can't see what's happening in this past view. It does kind of skew our graph though, so I do like to go to this raw Uekahuna station view, and I'll scroll over. Before I do that, we'll just point out our scale here on a vertical axis, microradians, 0, 2, 4, 6. So we're looking at 2 microradian increments. You kind of see our last deflation inflation went down from somewhere in a range of just under 2 to just under 6, so about 4 microradians or so before it picked up. And then the next one after that went from the middle here, so we'll call that 2, 4, 6 to 7 microradians or so. And the next one went down about 1, 2, 4 to 5 microradians or so. So won't be surprising if it does the same kind of pattern as we saw over here, right over here again, kind of coming back up, or it's a little more zoomed in there. All right, let's get back to that. And we can show you guys, kind of scrolling down here on the deformation page of the USGS, the GPS for the past year, that distance across a summit caldera from north to south, how much it's spreading apart, which is a proxy for how much it's filling and how much magma is pressurizing below. It's followed that kind of similar pattern, that big initial drop, and kind of increasing, decreasing in these kind of cycles. And we might expect now that we'll see it drop, and then that's the pattern we've been seeing kind of correspondingly on GPS, because the system is in such a state that the pressure seems to be moving the whole ground, and the GPS is picking up on that even at this sampling rate that it has. All right, so that's the overview. Looking back the past 5 years, that was all in here, and this is 2018. And not that anyone necessarily needs a reminder every time, but that's the context of where we are. Down the Pu'u'u East Rift Zone, we can kind of see there's still been contraction across the rift zone, similar kind of a distance measurement between two stations in a rift zone, and still going down. That's the interesting thing here. And likewise, the past 5 years, this was a 2018 eruption, and recovery and build up since, and you kind of see we have relieved pressure by going back down just a little bit here at the end. So in comparison, how much it's come up since, it's still not that much. And really, if we zoom in on the last year and look at this bulge that happened since June or so, we're not even quite back down to that level, which would be somewhere in here. So we'll keep an eye on where it ends up relative to that, just for curiosity's sake. But it's still upwards of there, it's still heading down at present. Okay, so and then putting it back in the context of the past few months, before our intrusion, so this is back in November, we had these deflation-inflation cycles. Let's see a few of them right over here. This was our intrusion event where magma injected a blade underground that didn't reach the surface. And we had more of these deflation-inflation events. You can see there's a couple more right over there. Then we have our December 20th eruption. North vent gets blocked. Back pressure, draining of the west vent, or relieving of the pressure of the west vent as it erupts lava into it, but without any draining. I shouldn't have said draining. And then here we have the big deflation, inflation cycles beginning. One, and then this tail end just picks up the beginning of the second one. So that's our tilt context on pressure. We'll go to earthquakes. If we look at the last week here, that's what most of the yellows are, is within the last week, and we see a few oranges in the last day, and mostly they're down here around the Pahala region, the feeder source, what we'll touch on some of our magma supply discussions today, kind of the deep source, right? These earthquakes are coming up. If I click on one of them, it'll tell me it was down at 33.3 kilometers down. You guys can't see that behind here right there, but that's what it says, 33 kilometers, 36 kilometers, 30 kilometers. Those are all the ranges of all these big, deep earthquakes in Pahala. The biggest one was a 3.1 that happened here earlier today. Some on top of Mauna Loa. Let's look at one of these. That one is above sea level, so it's pretty shallow, 1.9, kind of small, another 1.9, and then 1.8. So three in one day. That's our earthquakes per day, above 1.6 in that region. So kind of still slow for what it was doing before. There was one over here, 1.7, also Mauna Loa. And then also some south flank, we still have this 2.3 that's essentially in the same spot as that 4.1 we had a few days ago. So not a whole lot to talk about with the earthquakes as they're currently happening there. So we'll turn to our S1 cam. This is the last 24-hour time-lapse automatically generated by the Hawaiian Volcano Observatory. And you can see the west vent over here on the left. There's our fixed big island now, and where the lava streams around from the north and from the south, doing its overturning, its foundering, resurfacing the crust, but also kind of leaving that layering pattern that we were looking at a couple of days ago. So that is what's happening there, and we had, in our last update, a big spillover over this levee that was filling the trench on this north side, kind of all the way around the north vent, the remains of which are still over here, and come all the way over, kind of see the gray of it, ending right in there. So that seems to have stabilized. There's an overflow kind of right off camera here to the left. So we'll look and sit at the thermal, which is the view we're more used to. You can kind of look down here in the bottom right and see that spillover of this raised lava pond over its levee. It kind of bursts out right in there and kind of fans out into that trench area over there. And meanwhile, you still have the flow both to the south and to the north. Here's our north vent. North is about in that direction. Here's our big island. And you can kind of see that on this backside of it, we've been checking before whether lava is always meeting across there, or whether it actually at some points has hardened and solidified and made a little isthmus that connects them. So as we see the pressure drop here in the volcano, I'll be curious to see if we see any changes with that. If we see any changes with these little push-ups that are happening on the rim Lava is still squeezing out that outer edge at the edge of the crater, very, very slowly, not, very minor compared to what you see happening all in here. But you can imagine dropping all this new hot lava into the pool is going to be heating up and putting pressure and forcing some lava out in that direction. And when it finds that weak seam at the edge, it'll pop up until it kind of can re-heal that seam, right, by hardening in place. So you can kind of see this is the spot of our overflow 2 days ago over there, and it's all cooled off by now, and you still see repeated overflows that don't go quite as far downhill now. Now there's a new lava surface filling that trench. There's a thermal, and I'm going to do one extra review that we don't usually do today, and this is the Kīlauea West Cam. And here's the past 24 hours, and there's a lot of times that you can't see a whole lot in this camera because the wind is kind of blows in its direction. The thermal doesn't have that problem. But it so happens that today it's very windy. There's some windy weather across the island, and so the wind is blowing in the opposite direction. You can kind of see a little bit different. So here's our, same as our thermal view, our west vent at the bottom, our fixed island right in here, our stagnant eastern portion of the lava lake over there, and there's the lava going around the south and to the north. Right, and so this wind blowing a different direction is interesting. That's something that's we can document and look at the VOG forecast, the VOG map project. And what you can see is that the winds normally, for those of us watching who are not familiar with Hawaii weather, we normally have trade winds that are more dominant in the summertime and still dominant in the wintertime, but not as persistent, right? That blow from the northeast to the southwest across the island, with, of course, a caveat we have to almost 14,000 foot peaks that direct a flow kind of through and around, right? Kind of in all directions. Kind of smaller one over here as well, smaller one over there as well. So normally our VOG forecasts are putting the wind down towards these ocean view Pahala areas. But when we have Kona winds, it means the winds will switch and blow out of the southwest more in this direction. So you guys can see now all that material ends up to the north and east part of the island. And so we'll see that Hilo will have more VOG. Look at this plume right here. Right, as the wind shifts around, now we have all of it blowing to the northeast. So of course this is just a forecast and can watch it a little more, but it's a little more evident in some of the later frames. Kind of see how it switches around from blowing one way to blowing the other way. But let's look at our purple air as an indicator. And our highest value on a map is actually in Hilo today, close to Kīlauea at 30 ppm, I believe. Whereas unusually low, clean, clear air in Kona today, right? They're the ones living all that VOG blown out of there. Looks like today is a good day on the West Coast for air quality. And so we'll turn to USGS data once again, and here is SO2 measurements that have been filled in. This last part of the plot over here, we've got a flurry of measurements come in. So our initial values were upwards of 50,000 tons of sulfur dioxide per day, and it dropped down over the first 6 days or so to somewhere in a range of 5,000, 6,000 or so, and got as low as 2,500 down in here. And we've kind of had low values, but also higher values, possibly in relation to the amount of lava coming out of the vent, which is related to the pressure cycles, the deflation, inflation. Let me zoom that in so you guys can see that a little better here. And we had a big rain event, so data gap, but you can kind of see you might have had an up, down, up, if you believe those. And of course, they each have their little error bar, which is not plotted in this particular plot. But kind of see how that actually appears. All still low values. This is still 10,000 over here, so 5,000. Possibly 3,000, somewhere in that range, just based on the graph. Tons per day of sulfur dioxide. All right, and so when we look at the actual text report, when we can get more accurate information, we have here some observation in the last measurement, February 1st, 2,200 tons per day, which is lower than a long-term lava lake that was at 3,000. So it's on the low side, but it's still kind of that sustainable long rate, and we'll have to really see if that holds or if it still keeps petering off over time. especially in light of this current deflation-inflation, because there have been deflation-inflation events in the past that have affected like the nozzle at pool and cause lava to break out of a new vent at those points if it stays down and depressurized for long enough. That wasn't the case the last time, so I don't expect that to happen again this time, but we'll have to just wait and see what kind of changes might happen with the pressure cycle. And of course, the other measurement that's noteworthy on here is the depth of lava is 213 meters, 699 feet, just shy of 700 feet. And it seems to have been stabilized the same value yesterday and today. And that's possibly or related to these overflows taking the volume out of that upper perched pond, but also the fact that now we'll have a deflation event, and so we might have less lava coming in, and we'll have to see, how that actually manifests over time, depending how the pressure drops back down. So there's a lot more detail in here. You can kind of see that lava lake observations, they do say, yesterday, geologists observed that the vigor of lava stream fluctuated with cycles lasting 5 to 6 minutes. That's an interesting kind of that pulsation at the surface that we're seeing again, having been reported again. And likewise, another deflation-inflation cycle coming shortly afterwards. So that's the new info. You can go read it in more detail yourself. We'll switch to the more graphical stuff here. Here's the latest plot, automatic from the lava lake depth from the USGS. And so if I can zoom in here to this last little bit, here's where we've kind of stabilized with this last change in the pressure. And we'll have to see if we actually do any draining, like we see back over here in this section. If we stay depressurized long enough, will this actually go down? And will it go down from contraction in the short term? Will it kind of drain in the long term? We have kind of have self questions about what will happen there. But I still expect it to be short-lived and really to kind of just stabilize and then eventually resume going back up. Would be the probably most reasonable thing to expect at this point. All right, and here is the geologist measuring through the laser rangefinder the elevation right there below that western vent, and that's how they do it. And they're 213, 699 feet, also in the caption. All right, so there's you guys see all the PPE they're wearing in case of any unseen explosions or rocks being thrown in the air. You got your head covered right there. So this is what it looks like in a map view. This is a map release a couple of days ago, February 1st. And we'll zoom in, you can kind of see that's the trace of the new lava in the crater. And here's that upper block that's in the west that we're looking at, that's still way above the lava, the west vent being right in here, this kind of section, plunging in right there. And then the lighter colors are the hotter lava. So you can kind of see it's actually spilling over to the north in that trench during this particular thermal capture. Okay, and so an image was released by the USGS today. They're also now noting those same features we've been talking about in our thermal time-lapse coverage for some time now, and it's good to see it here noted. All these different features, the western fissure over here, the inlet, active lake surface, the levees we've discussed around the edges really mostly of this western part. Kind of have a new levee that's more in here now, right? And a series of cracks that kind of separate this rising middle of the western part. Presumably it's still bobbing up the island upwards, right? And this area over here possibly rising more slowly with lava ooze-ups out of the edge. Noted over here in terms of a warm ring, small ooze-outs along the perimeter, forming this warm ring, visible all around the outside. Right, you can kind of see that that's just this eastern half solidified on the surface, western half active lava on the surface. And there, that overflow, that northern trench onto the levee. All the same features, I'm just noting the validity of them here with the USGS labeled image. So another view, another couple images here to show you guys, and we'll kind of turn to our image portion of the broadcast before we take some questions from you guys, and go into our historical perspective after that. And we'll start with this aerial view of the lava lake, which is this darker color in here. It doesn't look red at all anywhere. This is that same upper western block I've been pointing out. That's kind of right above the western vent over here. And there's that island and the levee and that warm ring on the outside, oozing lava out there. So we can actually zoom in a little more. And you can kind of see the texture of the surface of the lava lake. It's really kind of hardened. If any of you guys have walked across Kīlauea, the floor of Kīlauea, that's the kind of features that this looks like to me right in here. You see that kind of hummocky, hardened lava surface. That's the result of the last overturnings of the lava lake. And you see these blocks kind of sticking out of it, like you see similar to Kīlauea from Pu'upu'ai, where it fell into the lava lake as well. And you had that kind of tephra material sticking out of the lava lake. So you kind of have a mini Kīlauea lava lake surface over here on this eastern part that still has liquid lava underneath. And this more active moving western half. And even then you can kind of see that the fastest, most liquid lava, hottest lava, where the skin is crumpling the most, is right in here. So it's a much smaller area, of course, than we've seen in the past. That's interesting. And a couple other things that they've noted in our photograph here. Right in here, let's see if I can zoom in some more. There's a rockfall. Looks like there's a little landslide of rocks fell down on top of this lava surface. And you can kind of see that lava has already formed a crust, and so while it's hot, it's not enough to melt these other rock falls until lava actually spills over from over here and then flows over and covers it up. That's how that goes. And some of the other colors in here, the white is steam. You can imagine that any water that's trying to approach this from any direction through this cracked ground is going to get hot somewhere not before it gets to the lava. It'll get hot back in this wall, and then it'll kind of come out as steam at multiple points. You do see some kind of more yellowish spots. Let's see if there's a good one in this image over here. Sometimes you see like more yellowish spots that are actual sulfur deposits. They're on a wall of the crater. There's some more yellowish in here too. It's hard to see with this particular exposure in a USGS image. So here's another view, and I can see down there a lot easier to see sulfur. Down here in the bottom right of this image. Here is that edge of the lava lake. That's that warm edge where lava is oozing out once in a while. And I kind of zoomed in on that hardened lava surface with the frozen small islands in it. These things were drifting around before. They've now hardened in place on that lava surface. And here's kind of the upper edge of that western lava lake now. It looks like it's spilling over in this zone. It's kind of pouring out, right? And it's feeding flows because this is now higher than over here. And we'll kind of keep going around. You can see that lava moving in a foundering motion around this island, and there's our west vent and that more fluid lava surface. You can really see that perched edge a lot better in this photograph right in here. And there's that rockfall, once again, right in there. Interesting little crack right here at the edge of this thing. You can see some lava flows have spilled over, and looks like little pohoi flows flowing on top of the hardened crust. Right, so that little piece of crust is lava flowing above it, and lava flowing below it as well. And there's that wider view there. And so we're going to feature this week 5 images from the Hawaii Tracker Facebook group, some of the great photographers that we have there. So we'll start off with, let's see here, image from Mike Mazul. I hope I pronounced your name correctly. And here he says, you can see he's zoomed in an aerial view of the old crater rim drive here. And we're all cracked up in the western fissure erupting down there behind it, pouring lava down into the lava lake. I'll let it clear here so you can appreciate its picture and its better unmarked glory. And next we'll feature a frequent contributor, Harry Durgan, Kona resident as well. And so here is his caption as the best show on Earth. And I see a really, really nice composition here. He's got the stars It's got all the gas illuminated by the glow coming out of the inner crater, and you can see all the steam in the upper crater cracks. Very nice composition there. Mahalo, Harry. And actually one more from Harry. You seem to want to reload. So here it is. Nice view from Andromeda. Kīlauea crater, February 1st. Next we will feature an image by Stephen Davies. You can see his Halema'uma'u Mauna Loa sunset and stars. Some fantastic images here. Thank you guys. We thought we'd feature some of these fantastic submissions that we have on Hawaii Tracker Facebook group. Hopefully you guys will submit those on hawaiitracker.com as well in the future. And here one to end on from Kalai and Delaries. And you can see a view of nice Ama'u fern here in the foreground. And uluhe plants, some native vegetation around here with Halema'uma'u glowing in the background. All right, Dane. So we're going to be talking about magma supply rates in a little bit here, but first let's do some questions on what's going on in the volcano today.
Yeah, before we get into the questions, we do gotta, thank Hawaii Tracker for, helping us get this platform going. HawaiiTracker.com is where we're going through. Three big ways to support us is the biggest way right now is to share this video, right? Like and subscribe, those types of things. That helps us get more traction. We don't have the advertising budget of a lot of these places that media companies, so this helps us get the message out there. Second way is to become a member on Hawaii Tracker, become a user there, become part of the community. Third way is through monetary donations, direct support, which is on hawaiitracker.com/support. We do have a few donations that I do want to call out before we get into the videos or get into the question section. So Brian B, Paul M, Lori H, Robin M, and John S. Mahalo, you guys. Really helps keep this going. And yeah, with that, we're going to the section Philip just did. We do want to make a little bit more of a regular thing where we're sharing some of this amazing photography that gets shared onto our track onto Hawaii Tracker from various, professional photographers, amateur photographers, guys with their cell phone that just, take a picture out the window. We get them all, and there's, some really amazing stuff. The one that we're having, I'm finding out right now as the stream's going on, is that it's snowing at the visitor center at 9,800 feet on Mauna Kea right now, which is interesting because that's pretty low. But, it was snowing on the saddle a week ago, maybe 2 weeks ago. So, right. So, yeah, let's dive into some questions. We got some good ones today. So, let's start with we'll stick inside the lava lake. So, Uncle Creepy on YouTube is asking about the Basaltberg Island raft, and is asking if it's like an iceberg in regards to there being significantly more of it below the surface than there is above the surface of the lava lake.
Yeah, that's an interesting question. Let me put the thermal camera back on the screen here. And yeah, I think a lot of times you imagine that it could have a bigger bottom than a top, right? But when I imagine how this thing actually formed, that kind of gives me some pause in the idea. Because really, this is like the chunk that was filling the very bottom of our ice cream cone, right? So the vent was at one point above the water lake, and it was spewing out all the cinder, and the cinder was falling in the water, hot, right, along with some liquid lava, but then it was filling in that kind of cone shape at the bottom, right? And so we actually had the bottom was smaller than the top to start, and of course, not all of it, became lava. The island, we don't know how much of it actually was, or how it actually moved or broke apart, from bottom to top, because there's a lot of steam in that initial phase of that that part of it, so it's really hard to see what's happening there in a lot of detail. But between that and the fact that it's been in the lava, and the lava can thermally and mechanically erode it, I would guess that this one may not have a bigger bottom on top, but it must have a draft that's deep enough that it's actually catching that deeper current of a lava lake, as we discussed in our previous islands and lava lakes video. It's been maybe almost a month now, maybe. But the small ones kind of float with a surface current, and the big ones seem to float against the surface current because there's a deeper current that pushes them in the opposite direction. So we saw that with the big island, especially. So that leads me to believe it is actually deep, but probably skinnier at the bottom than a regular iceberg. Just a guess, of course, because I really don't know. But the size of the island hasn't changed as the lava lake has come up. Really, it's kind of a similar size as it was when it started out, which was similar to the size of the lake of water that was down there. Which is, imagine that lake of water, the shape of that thing, maybe the shape of that big island.
Maybe.
Kind of
the one thing that immediately comes to mind to me is just like the density of ice versus water, right? And the buoyancy there versus the density of lava versus that pumice rock that we kind of think that this thing might be. Mm-hmm. So to me, I'd assume that significantly less of it would be submerged than with an iceberg. That's just my, layman approach to it, is that you would have less submerged, basically, just simply because of that. We do got some more here. So we're just sticking in the lava lake. What the two small islands are near the western vent? Are they not moving now as well? Are there any moving islands in there anymore, or are they all kind of frozen?
Let's see if we can zoom in here and get a view on some of these. It looks like there's one right here that's drifting a little bit. These are much smaller things compared to the other ones we've been talking about, but that's a size rock that is free, and some of these may come from that western vent, possibly down here when it breaks apart and gets clogged and the lava pushes some chunk out. So it looks like there are a couple that seem to be happily in place there.
All right.
This one seems to be moving a little bit. Yeah, it's kind of. There was a little bit of motion
in there.
Yeah.
Yeah.
Looks like this one almost bobs under and up, right? Kind of, it dips under and comes back up a couple of times. Interesting effect there. So all kinds of little details happening in there. So yeah, thanks for having us look.
So in 2018, the eruption was forming its own, weather systems over the Launi Estates, and we had all kinds of volcanic lightning and tornadoes and crazy things going on from that localized system. But has there been any volcanic lightning seen so far with this eruption? The only ones I can think of is in the very beginning.
Yeah, I think that very first day when you had all that steam rising all at the same time, that might have been the time. And I think I don't remember seeing any images of it, but I think I read something about maybe there was some flashing happening.
Right. I think I heard people talking about it, but it was only maybe during that first hour from the eruption onset until the lake was gone that was happening.
Yeah.
Sorry, go ahead.
Yeah, I was gonna say I think Matt Patrick's most recent part of his presentation, I think he said an hour and a half it took for that water to boil off.
Hour and a half?
Yeah.
Oh, okay. So one of the on YouTube, one of the questions is about the lava lake dynamics, and the question is do metals settle at the bottom? Right. I believe that's a question about just the dynamics of does the lava separate into different elements while it's in the lake, or anything along those lines.
Yeah. So what with the ingredients of the lava that you have there and the conditions, the temperatures and pressures that it's in, the most likely thing you form from this chemistry is olivine. And that's probably not surprising to those of us around here because it's all over the place, right? That's how you get your olivines. Of course, if they're sitting on the ground for longer, they get much, much bigger. So when you find big ones on the ground, they normally have been sitting on the ground for a while. before getting flushed out with some lava flow, right? So the ones that we're talking about forming in place now with this eruption are probably microscopic, that you couldn't see them. They're probably, you know, some fraction of a millimeter kind of thing. But they are forming, and they can, in fact, settle out of the magma and by gravity kind of flow down. Normally, that's a process that we imagine happens in a magma chamber that's more still, right? That doesn't have an active lava plunge point into it. So that could be churning it enough that you might disrupt that a little bit, but you might have some small scale settling of that olivine to the bottom. But that's something that happens very, very, very slowly. So it's not at the bottom yet, put it that way, even if it is kind of starting to move that way within there.
All right. So the last question about the lava lake I got here is about the surface temperature of the lake. What's like its range?
So I would imagine that when it's coming out actually red hot, that's in that range of 1140, 1160, 1180, you know, maybe 80 is a better end of the range to be at, since we're coming straight up from the magma chamber below. But I haven't seen an exact number reported yet. If we look at this particular image right here, we can see that the top of this temperature range from this infrared camera is above 600 or so. So what it's seeing as its hottest point from this angle, right in there, it thinks is 600. There might be some attenuation over distance, right? But, you know, that's what it's telling us. And, you know, we have in past lava flows, we can tell the temperature that the crust starts forming on top, you know, as tens, hundreds of degrees lower than that. And then when it forms this area over here is obviously much cooler. This might be more believable. This kind of purplish, bluish range, and more in a 100 to 200 degrees Celsius range for that hardened crust, right? Of course, there's all that heat coming from below it and through it, so you know, you might be a little higher than that as well from this distance. So that's the best we can do with this particular data. I should mention also, I think you're muted, Dane. I should mention also that, you know, that some of our viewers have mentioned like a pressure effect, right? That the actual lowest pressure on this whole lava lake surface is back near this vent, and that might be one of the reasons why these islands like to drift back towards it, because, you know, even when we had the north vent, we had islands drifting towards it. Right, so I mean, it might be something like that, you know, or there could be some, you know, maybe they're also deep and have catching some lower current. Those are the kind of candidates.
All right. There was one more question about the lava lake. Is the part that's solidified at the surface? The question is that strong enough that a person could stand on it?
Oh, surely. Like all this back part, you know, if someone were to
all that back part. If there's two Jedis maybe that were having a little fisticuffs, it would be okay. They wouldn't fall through.
You wouldn't fall through. No, you know, it's, you know, more a matter of like how long can you stand in the furnace, right? You know, and of course you could have some protective gear or some, you know, you might have the aid of the force perhaps, you know, but you need something to insulate you a little bit, you know, if you're going to be down there for any length of time, right? And it wouldn't be comfortable, right? You know, the gases, the actual hot air, trying to breathe the hot air, you know, might be an issue, you know. So I don't know about the whole biological side of things, but as far as could it actually hold your weight? Surely it could.
So we're about to get a little bit more abstract on the questions. First one is from Backyard Gardening on YouTube. Is there a chance that an eruption on Kīlauea could fill in the Kazumura lava tube again?
So that's a question that's come up in the past in some discussions. You know, it seems like a pretty unique case to have lava flow actually refill an old tube. The reason being that the lava is so much hotter than that tube it's going to try to go into, that to try to force its way into essentially like a frozen conduit is harder than going over top of the ground where you can you have no upper boundary. You can release all your heat upwards without being confined, and you can form your own tube above the ground. Is easier than filling an old tube underground. Now there's some caveats because, of course, depends how old the tube is for how hot it is. So
Right.
if you had an eruption going on, there was a few month pause, and it started going again, I could certainly see it refilling an old, feeling a tube that might be a year old even. That's essentially still hot. These lava tubes are in the first year too hot for any person to go into and actually go and sample and observe what's happening in there in detail. So they stay hot for a long time. Maybe in that case, yeah. Or maybe if you had a big enough flux rate, right? Enough flow coming out that's forcing enough pressure that you can kind of force its way through there faster than it can freeze. That kind of thing will be the other end of the scale of like how else you could do it. But that's pretty rare, right? Normally it's not going to go into the spot where it's got more pressure. It's going to go up where it's got less pressure and go to the surface again where there's less pressure. So that's kind of, that's why, and Kazamura is a few hundred years old, and so that's why I would be very surprised. It might fill in all the holes from above and fill in little pear-shaped.
Maybe for those aren't familiar with the lava tube, maybe describe it generally.
Yeah, that's there's a really. Let's see if I can find something. The Kazamura lava tube. So it's the longest continuous known lava tube in the world. There's a lot of qualifiers on there because there are longer collapsed lava tubes in other places like Australia, especially. But these are all intact, and they run essentially 22 miles in a straight line, and with multiple levels and multiple passageways that we believe lava was flowing through there during the Kīlauea eruption. In the 1500s, late 1600s, what is it, 1640 to 1680, I want to say, more or less. There's some error in there. So 400-ish years old, those lava tubes, and lava might have been flowing through there for, a few years, on an order of years for it to actually carve down the size channels that are in there. There's some areas that you have like an 80-foot tall ceiling underground, right? And just from the flow of lava, you have winding snake canyons and, all kinds of really, really interesting features.
All right. We do have a $5 super chat from Susan. Thank you guys for explaining things to this girl from Wisconsin.
Mahalo, Susan.
All right. So let's jump up to Mauna Loa real quick. Question from YouTube is Mauna Loa runny lava, or when it flattens out, or is it chunky? I think this is kind of a question of Pahoehoe lava flows versus A'a, and maybe the slope play into it.
Yeah, so there's different, I think of on Pahoehoe as two ends of a spectrum of possible large flow textures of lava flows, essentially, right? That's kind of they're all basalt. They basically have the same chemistry. One analogy I've used in the past is, you could have the same chemistry of things by having a glass of all the way liquid water and a glass of ice water and a glass of mostly frozen ice with a little bit of water in it, right? And if you try to pour all three of those, one's going to flow like all the way, one's going to kind of flow with chunks, the other one's just going to be a one giant chunk that doesn't go anywhere. So you can have the same kind of chemistry, different crystallinity, and you can have different kind of flow pattern, right? And that doesn't even include how much gas you can have trapped in a flow. So you do end up having A'a flows typically with higher flow volumes, with steeper slopes, and with bigger diffusion rates, right? The actual amount coming out. So you can have a flow start out as Pahoehoe, go over a cliff, and lose its exposed gas, and start tumbling and become an A'a flow. You can have the head of an A'a flow, the lava become more gassy and flow out through that same channel and turn that A'a flow into Pahoehoe flow. So it can kind of go back and forth depending on how it goes, right? So Mauna Loa usually erupts with higher rates and it has many more steeper slopes, so you typically see more commonly flows. In fact, most volcanoes in the world have that issue where they're slightly stickier lava, and you're normally going to see an flow. If you go to Etna, flows mostly, that's the kind of thing you see. But there are pahoehoe flows also. So let's take 1859 eruption. It went to Waikoloa from Mauna Loa off of the northwest radial vent. Right, it had an flow that took out most of the initial rate of lava and made it to the ocean in 8 days. From going all the way around Kīlauea, all the way to Waikoloa. And then that same eruption switched to pahoehoe, which went that same path, and after 200 days made it back to Waikoloa to make it to the ocean. So Mauna Loa can go either one. That north side is maybe the only place where it's flat enough to have a long-lasting pahoehoe flow. So that's kind of where that is. And
Right.
I did find this image right here this is the virtual lava tube. And you can kind of see a feature of, this is kind of just a generic image, but this is something that you see all these features in the Kazamura lava tube. Right here, you kind of have to come in through some just on the top, but you see multiple levels. You see places where you see lava chunks stuck to the walls and to the ceiling, lava balls. You see kind of big plunge pools. You see big plunge pools. Stop that again. And splash stalactites, drig stalagmites, lava blades from where the wind is howling out of there at jet engine speeds. There's all kinds of cool things, and there's some really cool lava tubes on Hawaii Island. You can see lots of these different features. So anyways, I won't go into that much detail. And on the surface, lava. This is the chunkier lava, and pahoehoe lava being the smoother lava for those that aren't familiar with those terms as well.
All right. So let's talk a little bit more abstract. We did have a question from Susan earlier, and question was, can fracking cause large earthquakes? And maybe discuss the fracking that and the earthquakes, as she asked it, but also maybe the differences between fracking and injection wells, and because Hawaii doesn't have any fracking in that way.
Right. So it's going to be harder to distract this. I don't have any images for this kind of ready, but
Right.
Fracking is something that is an injection of some fluid into the ground intentionally to cause cracking. Right, that's why cracking, right? It's fracturing the rock. You're intentionally cracking and fracturing the rock by pressurizing it below. That's good if you want the rock to have more cracks. If you want to have flow out of it of something you need, usually it's oil or natural gas. Right, that's natural gas kind of sits in layers in the earth, and you want to pull it out efficiently, and so that's why they do that kind of thing. Now that's different from injection. Injection is something that's been happening for a long time. An injection is essentially putting fluids into the ground without pressurizing them, per se, right? There might be some natural pressure from the heat that's down there. So a lot of times geothermal plants operate in this manner because they're recapturing steam at a different place. But they want to feed water down to generate the steam. That's kind of one way it's been done. It's also been done in other areas as a waste disposal, right? And that certainly can, where people will drill down a long way and and pump some, let's say, radioactive fluid or something like that, that you might not want anywhere exposed to where it will get to people again. So something like that was actually done in Colorado in the 1970s, where the Air Force was pumping water down, right in that front range of the Rocky Mountains. And over the next 2 years, I think the earthquakes in Denver went up by some huge amount. Earthquakes really went up by some big amount. And when they stopped putting fluid in at that deep depth, the earthquake stopped. So they directly linked the fact that putting in fluid in certain places at depth can cause earthquakes. And it certainly did that in Denver. Now, the situation in Denver... You have something to say, Danny? Jump in?
Yeah, I was going to say, how does the different types of... Just how does the, like, we have a bunch of lava basalt here, but in Colorado, what type of ground were we looking at? And how does that play into the whole thing?
Yeah, so when you have those big mountain ranges, you can have a whole range of different rock types, and it's more about where they're putting it in at that depth, right? When you're drilling all the way down, yeah. But there's certainly a bigger variety of rocks, including metamorphic rocks that are harder, and they also have looser sandstone rocks, in some areas. That's so it's really a great variety, and in Hawaii we're more uniform, and kind of the unique thing about Hawaii is that unlike Colorado, we don't have land on all four sides of us. That's really the biggest difference, to me, is the kind of what we call a stress state, like all the forces that act on that chunk of land. Like our island of Hawaii is one natural chunk of land, and there's nothing on the outside pushing in on it. And that's why the flanks can occasionally collapse, or they can kind of by gravity move outwards. We have our south flank on Kīlauea that moves away from the volcano and kind of just been creeping over there, like kind of continuously. I think it averages in the middle part of it 8 centimeters every year. That's long term. So that's just normal. Kind of naturally, Kīlauea means spewing, spreading. The volcano is spreading and spewing both, right? It's spreading with the flank, and it's spewing through its eruptions, and that's the whole magma south flank dynamic we've kind of brought up in the past. So in Hawaii, we don't have like a giant mountain range keeping that fault closed, and it's not going to move except once in a great while. And if you can kind of wedge some water in there and then widen that crack a little bit, then you can cause it to move more. That's kind of what happened in Colorado. When you have a situation like the South Flank, or by our geothermal plant in Puna, we don't have the rocks pressed up against each other like that. The one side is falling away continuously. That South Flank is moving away continuously. And that's why there's actually a natural crack that they're putting the water into it, and the water goes down and becomes steam. It flows through this crack, and it comes up where they know that the crack leads to the surface, and that's where they put the other well to collect the steam. So, in some situations, it certainly does. That's why the geology of Hawaii is so unique, is that we don't have that land to the south holding in the south flank to allow that pressure to have that kind of effect. But most places in the world have that situation, so that's why there have been links of power plants, geothermal plants, and earthquakes in places like Korea, or other places worldwide. That absolutely is all valid. It's a little bit different in Hawaii, and unfortunately that means that they can get away with using older technology as well, whereas we'd like to see all of our Hawaii infrastructure be the best and the latest thing, and that's just not the case in most of the time.
All right, so we do have a few more here. We'll try and finish these up so you can get into the magma supply from depth section. Yep. So with one of the questions from Mike on Facebook is about the lava lake and ultimately collapsing, and what about can you just talk to the dynamics of that a little more?
Well, I'm not sure that
he missed them.
Yeah, I'm not sure that it necessarily will collapse. It kind of it might contract and collapse a little bit on a scale of a few meters, maybe 10 meters, but nothing the size of the whole 700 foot deep pit. Like I expect it to kind of cool like a brownie pan or something, right? It might kind of stick at the edges, and it might kind of sag in the middle, and you might get like a little dimple in there, and you might get some cracks, and I get a couple low spots, but it's not gonna go anywhere really, right? So that's really, I guess, the shortest answer I can give as far as how it possibly collapses, right? More so, it should freeze in place and cool from the outside in and kind of stay gooey in the middle and kind of warm on the outsides.
All right. I think that basically does it so far. There are a few more questions I'll try and take care of in chat, and we'll get another round of questions for the end. But back to you and the historical analysis.
All right, and yeah, we can kind of gather these questions that we didn't get to even from this first half here at the end, if we're able to. So we're going to turn now to like just a little kind of a quick peek into kind of superficial view, but I'm going to expose you guys to a little bit of the information that there is out there on the supply rates of magma coming into the volcano from depth. So we showed you guys this image before. This is an image from Professional Paper 1801, Chapter 5. This one's by Mike Poland. And you kind of see here our main SC, South Caldera Magma Chamber, our shallow chamber, and our East Rift Zone over here. Southwest Rift Zone, kind of an area we see it seismically deeper, and an area that the lava goes into shallower, kind of called a volcanic Southwest Rift. And our scale here, the surface 0, and we're looking at 10 kilometers below the surface. We have this, what they call basal decoma. This is this detachment, like kind of the bottom of the volcano, where it can kind of slide sideways. That kind of stack of magazines, the base of that big chunk of it. And I'll show you guys this different view later as well. So let's go down to 10, and we also have the rift zones, which actually extend off of here like two big blades, right? Kind of like long sleeves and a long robe here, right? Kind of that go down and call it a deep rift zone, where the magma can go in possibly more passively. Who knows from which directions exactly it's coming from, but it can kind of fill, as this whole south flank slides, it can fill that area. So I'll come back to that dynamic a little bit later. But so we're going to zoom out a little bit here, and this is an image from Professional Paper 1806, which is another one we've leaned on in the past. And now our scale on the left, our depth in kilometers, goes down to 40. So before we were looking at 0 to 10, and that 10 level of that basal detachment fault is now marked as this purple layer, right? Kind of at the bottom of the rift zone. So the rift zone kind of goes as far down as that. That's a dynamic there of how that interacts, and kind of 3D there, right? With a kind of main hot zone of magma flow coming up through one particular area in that, and kind of feeding it up that way, and then possibly this way, and then possibly you get some going down, and possibly you get some, not quite sure, right? Exactly how that goes, but it seems to be detached here at that 10 kilometers depth. And then there's actually the pathway that goes all the way down from 10 all the way down to 40 kilometers down to what they call this deep seismic zone. So this is an area of magma generation of the volcano. So let me kind of switch this over, and we'll look at this kind of quickly to show you guys that you actually can plot earthquakes. This is earthquakes from 1970 to 2007 under Kīlauea. And the only thing different here is it's been separated by depth. 0 to 5 kilometers, 5 to 15, 15 to 20, 20 to 60, right? So kind of that's one way to look at it. We'll kind of zoom in on this inset over here where they actually stack them. Where did it go? Not sure what happened there. There it is. All right, they actually stack them. So here is our upper layer of 0 to 5 up here, and then 5 to 15, 20 to 60 down below over here. So you can kind of see that in a surface area, we see the pattern of the rift zones. Southeast, southwest rift zone is kind of an interesting southwest rift zone segment over there. You can kind of see that at that intermediate depth, 5 to 15, you see not the rift zone, but you see the south flank. And if you see towards the ocean from there, the south flank, right, with kind of a gap right where the rift zones go. Go down deeper to that 15 to 20 kilometers, and there's really not a whole lot there. It's actually an aseismic range for the most part, except for right at the core where it comes up. And we get down to 20 to 60 kilometers, that's where you have that wider zone right there. If you kind of look at how it gets dense, it kind of goes off in that direction, right? That is the one that goes towards that deep Pahala zone. Earthquakes kind of connect in that kind of fashion to this layer right in here. So that's where we get that structure from. That's where this diagram comes from. And so there's our deep seismic zone down here, that upper detachment that separates the rift zones. And we have labeled here 3 reservoirs: upper reservoir, reservoir 1, as the upper by right underneath the caldera, feeding the shallow eruption now. The deeper reservoir 2, the south caldera, and reservoir 3 is called this deep magma system. And so the authors of paper 1801 didn't include this diagram. This one actually comes from Kathy Cashman et al. From last year, describing how these magma chambers may actually look in reality. Rather than drawing them as like a single blob, one big magma blob, you may actually have various kind of pulses that kind of come up when they're buoyant, and then when I reach some level of equilibrium, they will fan out and form a sill. So this is what we call a dike, the upwards, the vertical part of it, and the horizontal part of it's the sill. So dikes and sills. So when people say a dike and sill complex, this is what they're talking about, is this kind of thing. So this may actually be where you have your more liquid magma. You can have different pockets of different chemistries, and then you have this magma mush that's partially molten, kind of surrounding it and kind of connecting everything. So when it comes to earthquake waves, that's what you can see the edge of, is this outer mush layer. But you actually can have multiple batches of magma within there of different chemistries. Right? So they've actually, in this diagram, applied it to more continental cases and increasing SiO2, which is the stickiness of the lava. Right? So all of our basalts are all at this end, and kind of mush and wall rock, and decreasing temperature as well. So these things will come into place, and then some parts might be cooler than other parts, depending on how recently they actually injected. So to kind of illustrate this effect of what's going on in here, but without having the benefit of this was published afterwards. These authors put in this kind of hatch mark zone right in here. I want to switch the color of my drawer, but can I see this hatch mark? That's our sill and dike complex all through there. And so they're kind of drawn schematically, kind of starting in 1950 now. Different batches of magma that came up through the volcano at different times. And so you can kind of see that the magma that's going to erupt in 52 is this blue one, and that's what's shown coming up here. It comes up in blue in 1950, and it parks itself in that lower caldera chamber. It also puts a branch to the rift zone, and it parks itself there as well. So this is kind of setting the stage for what will happen later, 52. And meanwhile, you have the so we'll advance here. And so we can see that in the period of 52, we've now had 54 magma come in from below. This kind of reddish stuff is kind of just filling passively and filling the magma chamber through here. And then something that's going to come out in 61, Hale already comes in 1950. And it sits possibly deep underneath the South Caldera, but mostly goes in the rift zone. So somehow it bypasses and doesn't really put a signal in the summit here so much. Our next increment from 52 to 54, we actually had an eruption in the caldera in 54. And you can kind of see here the red arrow showing that fairly quickly from depth, this patch came all the way up and erupted on the surface. Right? That's the kind of thing we don't have happening now. When we had our initial results of the magma chemistry, we learned that the magma we had coming out in this current eruption came out from having sat here for a while also, and then popped out. Similar to some of these other magmas that are coming up years ahead of time and sitting in the ground to feed the eruptions. So that's how it often happens, but sometimes, like in 54, you see it actually comes all the way up from some deeper depth and feeds that summit eruption and intrusion. Okay, we'll advance another increment here, the next year from 54 to 55. So in that time, that 61 lava is just sitting there in the main caldera, and it's also moving into the rift zone a little bit more and causing an intrusion over here under Kīlauea. In the meantime, in 1967 to 68, lava will erupt 12, 13 years later, starts coming up in purple here. And we know it's going to park itself over here at some point, but it's also first going in the East Rift Zone over here. That's the next increment in time, so 54 to 55. That's that kind of period happening there. You can kind of see that it may be the pressure of this magma that eventually comes out in 6768 that goes in the Rift Zone. Over here in 1955, it's now the third magma body in the Rift Zone, right? So we have 67, 68 stuff will erupt. We have the 61 stuff that's going to erupt that actually popped up over here. We have the stuff that 52 erupted. And this stuff is moving up, and you can kind of see in 55, we're going to have the lower East Rift Zone eruption. It's going to happen as a result of all this Rift Zone taking these batches of magma. Okay, so from 55 to 1960, we have that purple batch coming up still. It's kind of filling the Rift Zone even more over here. Meanwhile, the 55 eruption is over and it's kind of still cooling underground. Some of that lava will get remobilized in 1960. But first, what causes 1960 to go off in the first place is this Kīlauea lava. And that's coming from this black zone from way down at 40 kilometers down. And this is coming up. This is not exactly the path it took necessarily, right? This is like a vector showing where it started and ended with no known stops in between. So it may have come up along the side. But however it did it, it popped out of Kīlauea and it was detected. And this is detected by those kind of earthquakes and by those chemical signals as well. So it came all the way up in 54. 60 to 61, you can kind of see that the black stuff ended up all the way to Kapoho, but it probably came up in a path Waikiki and then back down to the Rift Zone, out of Kapoho that way. It's a more accurate path. But meanwhile, you see that the 67, 68 batch is now pushing up on the 61 batch, and the 61 batch finally erupts. 61, it's the same thing that it was intruded earlier, over under Kīlauea. 67, 68 is that purple batch, finally, that's been sitting under the summit for a while, but you have labeled down here what's going to be many magma batches coming from the mantle during the 5-year eruption of Mauna Ulu, and kind of that continuous increase in magma supply right there is going to be what pushes this batch of magma up. And so what we have going on now is probably not that unlike this, right? We had some of the magma that was in the summit went into the Rift Zone as well, right? There's probably some batch of it on the surface over here, right? But it's really the continuing pressure of magma coming from below, all these many, many batches from below, pushing what was here before up and out. And so depending how long the eruption actually lasts, you may see a progression of chemistry from what's been sitting here to what's been pushing it at some point in time. It might have to go on for months to a year for that to happen. But that's something that may be the case. Okay, so kind of a couple of other things to show you guys. This is a similar version for Pu'u'o. When Pu'u'o began in 1983, we had that batch of magma from depth coming in from the side, but there were 2 pockets of old magma, one from 77, that got mixed into that initial series of fissures before the more hot, juvenile, pure magma took over as a main source, and then eventually created that barrier, which is what kind of lasted until 2018. So even Pu'u'o had that similar kind of chemistry. And of course, we've discussed in the past the 2018 chemistry, how the lava that was feeding the lava lake drained out through the Rift Zone, past that blockage, and then came out in the lower East Rift Zone, pushing out perhaps 55 lava. Some older pockets, Fissure 17 might have been something from possibly 1790. There's also 1840. There's also 1924 as candidates in there. And other little pockets of lava, of magma, kind of also all scattered through there, so who knows. So that's kind of the story, kind of rounding it out. But looking long term, scientists have looked at all these different patterns, and they've come up with different rates of magma supply for the volcano over time. And so I've kind of compiled 2 plots here from a professional paper, and I've got 1823 back over here, and 2018 is off the plot over here. But the general pattern is we had very high magma supply back in the early 1800s, and it went down by around 1840 or so. So 1840 was a big caldera collapse, and that was, you know, an interesting shift, right? That kind of went down, and it stayed at a low level until around 1950 or so. And around then is when it starts going back up, and then really 2003 was when the latest batch of magma comes up to feed that Summit lava lake, Summit eruption, and eventually to 2018 eruption. That kind of begins back over here in 2003 was when that lava starts building up. So when you see a pattern like this, right, you might think, okay, well, maybe really the only thing to compare to these high magma supply rates is anything that happened back before 1840, right? When we had caldera collapses in 1823, 1832, and 1840, but the previous two, with high supply rates, they refilled very quickly. We don't see much detail of that era in time, but we see the increments that we do seem to indicate that. And to kind of show you guys that, let me see if I have the right image here. No, this one. From the Roadside Geology of Hawaii by Richard Hazlitt and Don Hinman. We'll zoom in here on these caldera maps, and so you can kind of see after the 1823 collapse, we have a deep pit in the middle. And by 1829, no more pit. That whole pit was all the way filled in. By comparison, our Halemaumau pit today is only maybe a third of that size. It's about this big, right? Whereas this earlier pit was the whole caldera, and the whole thing got filled in the next 6 years. So possibly there as well. You see 1832, the big pit is back. Another big collapse pit, but with kind of a big gap in time past 1840, we can kind of see it was refilled. In this case, you can't really tell how fast it refilled, right? But really, this sequence right in here, 1823 to 1829, shows you how much volume you could fill a big hole, how quickly. And we don't know if it was continuous or lots of small eruptions, and that's kind of where the big question mark is, what happened in those 6 years. But could be 6 years from now, we don't have a hole anymore if this thing goes at that similar kind of supply rate as we see back over here, right? 1823, here's the 2000s, yeah, even higher. And kind of explain a little bit more here. There's a little bit of blue on this diagram. The blue is trying to incorporate the south flank movement, right? So when the south flank is moving, like, is it actually, you can kind of see the south flank starts moving more in this era, and maybe that leads the increase in magma supply a little bit, right? The south flank moves a little more in 1975, and then magma supply rate after a little while increases more. I don't know. It's interesting to kind of look at those patterns a little bit independently, and that's why it's plotted on here as well. And each of these numerals is on here. So sometimes caldera collapse can change things a lot, right? This 1840 collapse maybe was caused by the drop in magma supply, but who knows, right? So that's why we don't know when we see a big caldera collapse, does it mean a drop in supply or not? And it seems like now, as this thing drags on, it seems more likely to me that we're kind of continuing this trend on this end. So how can we look into that a little bit more? Well, we can look at the ground tilt and GPS plots for the eruption of Pu'o'o. So Pu'o'o had been inflating, and then when it begins erupting in 1983, it starts deflating and deflates all the way until 2003. It's the first time it's actually switches course. And that's, if we go back to this graph that we're just looking at, 2003 is right here. Right? So from 2003 onwards, higher supply rates. And you kind of see that as an initial pulse, and then a whole turnaround, and the whole trend of the graph starts going upwards until 2018, when it drops back down to eruption. Right, here's a GPS, similar plot, spreading, and then eruption, right in there. So what happened past 2008? Well, the magma was still coming in at that high rate all through here. That's the evidence that we see, is we didn't see it turn around at any point in time. So since eruption began, actually ended in 2018, GPS has come back up, right, until we saw a little decrease now here. And so that's kind of what we're looking at, as that pattern there. And that's why it's important to see if the GPS long-term is going down or is going up. Because if it's going up, then that tells us something maybe more about our supply rate and how long the eruption may last. compared to it going down, and maybe it won't last quite as long. So here's an image from a paper by Mike Garcia at University of Hawaii Manoa, and he's kind of shown how our current configuration, when we have high magma supplies here on the left, we actually can sustain 2 different magma chambers and an east rift zone feeder all at the same time. This was, of course, published prior to 2018, but you can kind of see that, right? You can have that much magma filling all that zone, whereas in the epoch of 1912 to 54, with low magma supply, you didn't actually have evidence of magma chambers. You had some eruptions that came all the way up and through and didn't touch any stored magma, and others that kind of came up and contaminated other later sources that came through them, and others that kind of went through some parts, then had different chemistries from then. So a lot less connected in the summit in those low supply times than in the high supply times. And so the fact that we do have still an upper shallow chamber and that lower chamber, and we still had magma filling the east rift all the way to Pu'o'o, does put us more in a camp of this high supply rate still, an eruption lasting longer, or if it does end, that it will have another one shortly. It will kind of keep doing its thing, refilling on and on and on. So we'll kind of, that's the end of that. And I'm trying to get back all the way to where I started our discussion today with the GPS, right? So here's a GPS for the past year here. You kind of see it's been a steady up and building to eruption. Eruption relieved it, but then since the eruption began, it's been an upward trend, and that's why we have to really, really think about that as being the long-term trend potentially. So maybe a little bit too deep, but sometimes we like to go there and dig at these questions of where the magma may be coming from, how long it might be sticking around, and that kind of thing. And we can talk about some questions.
Right there.
Yeah.
Yep. We have a $5 super chat from Two Pineapples. Aloha, mahalo for everything you guys do. Appreciate it. Well, thank you, Two Pineapples. So we do have a few questions here. Really, the chat has just been mostly still about fracking and things along those lines, and just the dynamics on that. But there has been a few questions that came through. Mm-hmm. This one I actually like. It's not going to really work at Kīlauea, or at Hawaiʻi per se, but maybe going a little bit of an explanation on the formation of pit craters and sinkholes in the years to come following volcanic activity.
Yeah, so I mean, it's always possible when magma is moving around underground that you form some sinkholes, pit craters, right? There's essentially a pit crater is a collapse feature like a sinkhole, right? You know, a sinkhole more often is termed for somewhere that has like a limestone or a karst kind of ground, like somewhere like Florida. And in that case, it might be water moving underground that actually dissolves or erodes or whatever that causes a collapse on the surface above. So a similar kind of concept, but in this case, a magma is what's moving underground, and a magma is leaving some area that it was filled before. And when it does that, then the ground falls in above it. So the question really is, where do you have those larger magma storage areas that could collapse, right? And so we look at the eruption of Pu'o'o. Pu'o'o is a clear candidate for that. That was an area that had a big, shallow chamber, and Pu'o'o, if it keeps, like, can I go back to my tilt plot or GPS plot that I have here? It keeps collapsing together. If the edges keep getting closer and closer together, then this might be the signal of eventually falling in, right? It's way too early for that. It's only been doing that for like a month, but that could be what happens at Pu'o'o if this trend doesn't reverse, right? Now, like we just talked about on a East Rift Zone, if it's connected to the summit in this high supply rate scenario, then this thing should turn around and refill as part of the magma chamber once that happens as well. So interesting that we have at the same time, a contraction on the East Rift Zone, and an extension at the summit, right? So that's kind of showing us that maybe that flow from Pu'o'o, even if the summit is pressurizing, it's doing it somewhere not connected to Pu'o'o because Pu'o'o is not feeling it. So it's kind of interesting. It might be a separate little batch in a separate little zone than what was actually feeding Pu'o'o. And that's kind of an interesting thing to think about there.
All right. One thing that's interesting to me is just the giant collapse pits right outside of Leilani Estates. I think there's like 6 or 7 out there. And to think that how much magma storage was in that area. Very clustered collapse pits. And how far it is down the rift. It's pretty incredible.
Yeah. So those may have a further complication, which is that you could also have groundwater explosions, and some of those pit craters show evidence of explosive activity, right? So it's been speculated that many of the pit craters formed when you had a lower supply rate and a movement of the south flank. So something that would have also caused a big caldera collapse, right? So maybe when you had the 1500 AD caldera collapse somewhere in that range, that you had some big south flank movement, you had the groundwater going, there's magma in the rift zone everywhere, and wherever there's more of it, it's going to explode more, possibly, right? So you might have just had explosions that happened, and possibly you had many pit craters on the East Rift Zone forming all in very short sequence in very short time,
right?
And
and that's kind of why that area gets linked to the 1500 eruption. A lot of areas, it seems like, kind of get linked to that one. We don't know if it was how the duration of that eruption is kind of vague, but it seems like it was a very big event. Don't know how long it lasted. Could have been in parts or one continuous event. That's the interesting part.
Right. We think that that's the one that kind of forms the that main outer caldera fault structure. Right. So like that great caldera, that biggest zone that you see that includes all of Keanakakoi and all of Luamanu in it as well. Right. That size collapse. Golf course. Yeah. That size collapse, then now you're talking about something big happened.
Right. So Daisy asks, I know Fisher. Oh, we have a $9.99 super chat from Jay Roller on YouTube. No comment. Appreciate it, Jay. He says that he appreciates us. All right. Daisy asks a good question here. So she says, I know fissure eruptions are common on shield volcanoes, but can they happen on stratovolcanoes too? Do stratovolcanoes have rift zone, or does the magma just find a path of least resistance?
So that's a great question. I don't have the details on the different kinds of volcanoes. I don't have an example that I can cite you right now. I do believe that there are some stratovolcanoes that have some kind of rift structures to them. They may not be as long as our Hawaiian volcanoes, but the biggest difference with the volcanoes is the magma composition, and that's really what drives most of the difference, is the fact that you have more silica in your magma, and that extra silica makes the magma more viscous, more sticky, so essentially gas bubbles can't escape it as easily, which means that they form bigger bubbles and form greater gas pressure within the magma, right? And that's what causes greater pressures for that eruption. Whereas normally the magma temperature is lower, you have more. You can reach that same pressure by having a gas kind of building up more over time, and it kind of goes off with a big poof. And depending on the structure of the volcano, it may have unstable flanks. You could have the flank slide off, like in St. Helens, the north flank slid off. But I don't know if you'd call that like a flank. I mean, a rift. It's not exactly a rift zone. It was like a failure of the actual outside of the rock holding the magma chamber in. So when that fails, then the magma can shoot out in that direction because there's the relief for all that gas pressure, and that's mostly why the magma erupts differently in those areas, right? Some places get very complicated. You can actually have basaltic volcanoes and more silicic volcanoes, like stacked one on the edge of the other. So certainly you can have some complicated magma pathways, especially in places like East Africa, where you have the continent actively spreading apart and a new ocean is going to form there someday, and kind of have that mix of the continental rocks and continental magmas and the rift magmas all mixing and all in close proximity. So it can get really complicated and messy, you know, and maybe I can find a picture of another stratovolcano with rift zones, or if someone in our audience knows of one for us to look into, then you can drop it in the chat as well, and we can maybe get it on the screen for you guys.
There is a few comments about potentials. One of Derek mentions Mount Shasta and the Dacite Lava Dome, Black Butte, some distance away, as being a potential candidate. Novarupta in Alaska, I'm probably pronouncing that terribly, but you know, that's what I do. And let's go on to the next one.
Yeah, I mean, let me just say one last thing here. Let me put this earthquake map on here and just kind of say that, you know, the Earth is a sphere, and it turns out that when you try to puncture through a sphere, like the easiest way to crack a spherical surface is with, you know, 320-degree angle spokes. That's kind of how you relieve pressure on a sphere. That's just, you won't get more complicated than that. So quite often volcanoes do, you know, any kind of structure in Earth, volcanoes do have that kind of, they want to be that shape, right? And even Mauna Loa, that has these two southwest, northeast rift zones, does start having radial vents off to the north. So Kīlauea only has two because of Mauna Loa, but it's interesting to think about what might happen with its north branch. Kind of Mauna Kea ends up being in that direction. So they kind of stack on each other, but I wouldn't be surprised to see some of these structures, you know, maybe, like I said, not as long as something like Kīlauea, because Kīlauea is east rift. Let me turn on the layer here for ocean, because Kīlauea, and zoom out, because Kīlauea is east rift. It goes farther offshore than it does onshore. These things can be massive. So let's see what other questions we can get there. So there are some effects of all that lava building within the pit and weighing down, and it may actually cause some little tilting, but it also might be pushed from below and might cause a little tilting. It's interesting to think about that little rockfall we saw in that image earlier. And where, you know, what caused that instability? Where is it? In order for it to slide down here onto the surface of the lava lake. So one thing we mentioned in the past is that some of the previous islands and lava lakes have been formed from tilting on the ground, and so it may be that's something that certainly can happen. Rocks can fall in here. If it were to hit an area that has a thin crust that's forming, it could certainly break that crust and induce an overturning event in that area. That's something that's been seen in the past, Mauna Ulu and other eruptions. You know, you can find videos of volcanoes all over the place. That once you kind of break that initial surface, even Hale-Maumau, once you break that, then you kind of allow the gas that's built below the crust to start churning. You kind of induce a spattering effect in that area. So that's certainly something that might be in the future for us as we look at some of these pictures and think about the ground moving and things falling in. Another question, Dana, you got picked out?
Yep. Next one is from Karen on Facebook, and she's asking you to talk about the 1790 explosion at the summit a little bit. The summit of Kīlauea.
Oh, I can talk about it a little bit, but you guys should go and listen to the Don Swanson virtual field trip when he's standing in front of the deposits and talks about that.
Uploaded on the channel.
So yeah, that's on our channel. You know, if you want to kind of skip there to like the last third of it, more or less, that's where he talks about 1790. But I'll kind of review and recap a little bit there of what he said, right? So 1790 was there was a big explosion that was lethal to some Hawaiian warrior party that was nearby, and there's a lot of detail to that part of it that maybe you can go listen to Don on, right? And I'll kind of try to stick to the geology part of it there. But it seems like there were quite a few southwest rift zone eruptions and summit collapses in the southwest rift zone eruptions and critical collapses, like from 1790 through the early 1800s. And a lot of times we wonder if that might be what actually allowed there to be water interaction, and maybe there were steam explosions from that kind of, we feared in 2018, but maybe that actually happened in 1790 from a southwest rift zone. It's hard to tell. We do see that those explosions brought up fresh magma all the way to the surface. So it could have also just been magmatic pressure. It could have been you had just building gas in there, but we don't see with today's dynamics how just building gas in there wouldn't cause you to just kind of pop it erupt like we see here, rather to explode it with that massive explosion and cut or collapse that went with it. So, but there's essentially were some very big ash explosions that were visible from Kīlauea on the northwest side of the island over top of Mauna Loa. So for someone to see the ash cloud rising from behind Mauna Loa, which is nearly 14,000 feet high, from 30 miles away, you can do the math, and it ends up that cloud had to be somewhere around 30,000 feet high, at least. Right? So that kind of explosion dynamic is what really drives a lot of understanding of the 1790 eruption. Right? That, and, there's a lot of, even as far as the people, we're not sure how many people actually died, because that's how diverse the historical records are. Right? So it's really hard to get specifics on that time. But Don has gone through and analyzed all those different layers of tephra, of fallout from explosions, not just 1790, but all the way back in time through the 1500s and even further. I can tell you, okay, this one, maybe more water, maybe less water is something that they're looking into now. Looking at the kind of glass chemistry of that stuff with the new staff member since last year. But really, it's that how big is the lava broken up? Is there fresh lava, right? When it landed, did it land wet, right? So 1790, we know that there is a layer of wet, ashy mud, right, that has footprints embedded in it that have rocks from a later eruption, later explosion of the same eruption embedded within that ashy mud. So explosions, that there was a first wet explosion, and then at some point not long afterwards, there was an explosion with bigger ballistics that landed and fell into that ash. And in between that time, people were walking around, leaving imprints in the wet mud, likely because a bunch of people had died, and they were going to try to rescue or assess or see what was going on, right? All the family members. It's hard to say exactly, right? But Don does mention that a lot of the footprints are from short people, right? Presumably females and children. So families that will be coming and check on the area. So it's a complicated record there. There was an explosion that had wet ash, then several other fallout explosions as well. We would describe it as big enough to have that pyroclastic base surge. That's what actually killed the people, was the fallout of ash at hurricane speeds, hot rock displacing all the air and kind of searing people, but not burning anyone really that badly. But probably mostly displacing all the atmosphere from that whole area all around where the ash cloud was collapsing around the volcano.
All right. We got one last one here for you. What about what effect is the weight of the lava having on the stability of the surrounding area?
Yes, I think that there probably is some effect. If we could see an INSAR, or we could maybe see how what the pattern of the effect is. In theory, it should be kind of concentric surrounding that lava lake as it kind of weighs the ground down. But also we have a rising on one edge of it as magma is kind of pushing up. So you could have some tilting going on there. That's something that's going to be hard to pick out from that tilt signal possibly that we have, right? So that's kind of interesting to think about what kind of background tilting might be superimposed. But the lake surface is a pretty good indicator, as it's still liquid and filling, especially on that western part. If the western part ends up kind of at a different angle as everything else, we'll know that it is tipping. But that doesn't seem to be the case. It seems like it's coming up pretty equally, spilling over both to the north and to the west, and to the north and to the west. And then the east side is a whole other story. So that's basically it. It's more about, is there going to be empty space below? And it's probably not, because as you relieve that gas pressure and you're still feeding magma in below, just a matter of when you hit that equilibrium again. And if you do that, if you can kind of keep erupting or not. So that's a little bit.
Yep. Well, that does it for me on the question end. Appreciate everybody that came to it and contributed by throwing out their question. Some really good ones today. And we are brought to you by Hawaii Tracker, hawaiitracker.com. Make sure to like, subscribe, and all that fun stuff. And I appreciate it. I'm out.
All right. Mahalo, Dane. Mahalo, everybody. Submitted questions. Mahalo, you guys who are contributing and donating. We really appreciate it. And for hawaiitracker.com, for Dane DuPont.
One last super chat. Adam Gafford. Thanks for all the wonderful info. $4.99. Appreciate you.
All right, Adam snuck in there. Mahalo, Adam. Thanks, everybody. For Dane DuPont, I'm Philip Ong.